Let me first thank Professor Raja Jurdak for having accepted to deliver a keynote today for at the Wireless Days conference. So Professor Raja Jurdak is a professor of distributed systems and chair in applied data sciences at the Queensland University of Technology. He's the director of the Trusted Networks Lab. Raja received his PhD in information and computer sciences from the University of California, Irvine. And he previously established and led the distributed sensing systems group at CSIRO Data 61 in Australia, where he's still having a visiting scientist role. He also spent time as an academic in multiple institutions, in MIT in the US, in Oxford University. He was previously also at UCD. There, I knew him there back in 2007, 2008, if I remember well. His research interests include trust, mobility, and energy efficiency in networks. He has published over 190 peer-reviewed publications, including 2 authored books. Most recently, one on blockchain in Cyberphysical Systems. He serves as well on the editorial board of the Ad Hoc Networks Journal, and he also was part on the organizing and or the technical program committee of many of the top conferences we have, including PERCOM, ICBC, the newly established conference for blockchain and cryptocurrencies, IPSN, WOMOM, ICDCS, etc. He was, by the way, the TPC co-chair of the ICBC in 2021 in Sydney, Australia. And he is a conjoint professor with the University of New South Wales and a senior member of the IEEE. We are really glad to host today, even though remotely, Professor Raja Jurdak for speaking about blockchain for cyber-physical systems, as he's one of the leaders of the topic with many highly cited publications on this domain. So please, Raja, you can start and share with us some of your experiences on this topic and some of your knowledge. Thank you very much for that.
All right, thank you so much, Yassine, for the invitation and the opportunity to speak to the Wireless Days community, and thanks also to all the organizers of this conference. So I will be talking about blockchain and cyber physical systems and our work in this area. What we mean by cyber physical systems typically is when there's a tight conjoining between the physical and digital world, when you have sensors getting data from the physical world, communicating them in large-scale distributed networks into cyberspace, but also taking decisions where you might actuate and change the state of the physical world. And obviously, to have large-scale cyber-physical systems, you need large-scale networks as well. And that's where IoT comes in. Many people use the Internet of Things and cyber-physical systems, the terms interchangeably, whereas IoT typically focuses more on the connectivity and networking aspects. And there's a clear significant growth in the number of IoT devices globally. There are different estimates if you look at different companies and organizations, but it's clear that they are in the tens of billions in this decade, and they're constantly growing and taking a larger proportion of the share of connected devices worldwide compared to non-IoT devices such as computers and phones and all that. Now, this scale is really useful to get a lot of information from the physical world, but it also produces a large volume of data. Whether you think of connected vehicles that can produce, an estimate is 25 gigabytes per hour from all its complex sensors, or going to other complex systems like jet engines, wind farms, where you really have scales of data being generated and transmitted that are unprecedented and are growing exponentially. And that obviously creates, while the data has a lot of value, we know that it creates challenges for scalability. And one issue with scalability there is that the current or the conventional approach of centralizing data management and data storage doesn't scale. So when you have to rely on the conventional client-server paradigm, you're always sending data towards a central server where devices are identified and authenticated. That doesn't scale when you have a very large network, as the IoT is becoming. And as an example, two IoT devices, sometimes when they need to communicate, they might be physically close to each other, but then in order to communicate, they might have to go through a gateway or a server. So another issue with the current state of cyber-physical systems and IoT is that security and privacy, as we've been hearing a lot on the news. Many of us would have heard about the Mirai botnet issue a few years ago, where a distributed denial of service attack was created by hackers that simply hacked into smart home devices, including cameras and other smart home sensors, in order to essentially generate so much traffic to deny service from critical services for large companies in the world. And more recently, we also heard about some of the attacks on critical infrastructure in the US with the pipeline and other critical infrastructure like supply chains. In those cases, they were it was ransomware where the attackers were trying to get money from those companies. But clearly, there's a vulnerability there in terms of the security of these cyber-physical systems. And also, when you are sharing data from people or businesses, local context, there are many things that are private. So privacy is also a challenge. Now, another issue with the centralized conventional model is that you have data silos. So organizations tend to be very protective of their data. And also, once users or participants give their data to a server-based organization, then you have limited control over how the data is used or how it is stored. Essentially, we have to place nearly absolute trust in the cloud and application providers. And with IoT devices collecting highly personal data, whether from your home or about your energy consumption or from your smart vehicle, the fact that we have to place all that trust in a central trusted third party is an issue. So just to recap the challenges facing CPS, clearly we have heterogeneity in device resources. So we may have very computationally constrained devices to more capable devices. There are many attack surfaces ranging from the sensors themselves to the communication medium. And scale is an issue. So centralization is not the ultimate solution there. And we also mentioned the lack of control over how data is used and shared, and lack of visibility over what's happening with our data once it's there. There are also very complex interactions relating to the firmware that's installed on these devices, different versions, and who might have produced them, and what backdoor approaches they might have, which raises a whole bunch of security and privacy mechanisms. So in our research, we saw these problems, and we were thinking, is there another way forward to address some of these considerations for cyber-physical systems? And as if you've seen the title slide on my presentation, we've been looking at blockchain as a potential solution for some of these challenges. So some of you might know this, but blockchain essentially was introduced in 2008 as underpinning the first cryptocurrency, Bitcoin. But in essence, it uses a lot of basic computer science constructs, including linked lists. It also uses asymmetric cryptography, private and public key infrastructure. It relies on hash functions in order to turn data of arbitrary length into fixed length hashes that can be easily summarize the state of the database. And it also uses a peer-to-peer network. So blockchain, in essence, is a distributed network of computers that is managing the database together. And then there are incentives to encourage these computers to commit the resources for managing the database. Because typically when you have a centralized organization, the incentives are that this organization has some business model to make money from storing data and providing services. So the incentives are built in. But when you have potentially thousands of computers around the world managing the blockchain, they need to get something back. So incentives are key to the sustainability of a blockchain system. So all those basic contracts, essentially what they lead to is a shift from centralized databases where which have their own validation rules. So where all the clients connect and they provide their data to the centralized database. And that requires, as we mentioned, a very high degree of trust in the operator of that database. So blockchain moves towards a distributed database where any computer can participate in storing and maintaining the blockchain, and these are the validators in that model, and that becomes a distributed ledger. So the idea is all these validators, they would store a copy of the state of the database, the blockchain, and then they agree on that state using a particular consensus algorithm. The most popular one is proof of work, which is used for Bitcoin. And so they agree on that state. And because of the linking of consecutive blocks in blockchain, so every block has a hash of the previous block. So the blocks are linked together in a way that if you change any transaction or block in the past, that can be caught by all the other validators. And so blockchain is an immutable distributed database. And through this way, you have a lot of transparency and auditability in the state of the blockchain. And you actually don't need to trust any of the validators because they're all kind of monitoring each other. And that's the beauty of that approach, which opens up a lot of possibilities for different applications. Now, one thing to note is that many of the conventional consensus algorithms for blockchain are usually computationally heavy. So proof of work requires solving quite a complex puzzle and spending a lot of computational resources to do that. So just to recap on what we mentioned about blockchain, it's a distributed ledger technology. It provides chronological and time-stamped records of the database. It is immutable, and as we mentioned, because of the linking of consecutive blocks. And that provides a high degree of auditability where we can look at the past transactions and see exactly what happened and have a high degree of trust in that because of the immutability property. And the immutability property is cryptographically sealed with those hash functions. So there's a famous decision chart that you can see on your slide that was proposed by Wust and Gervais. And this is asking, is blockchain indeed the answer for a particular problem? And they came up with a very interesting set of decision points where people can look at it and say, all right, blockchain is a good fit for my problem. And essentially, it goes through the steps of asking if you need to store state about for your application, if there are multiple writers, whether you can use an online, an always online trusted third party, and whether all the writers are known. Now, if you take that first branch in that decision chart, and you answer yes to the first two questions and no to the second two, then you do need a permissionless blockchain. However, if you go through any of them and you break away from that branch, you actually probably don't need a permissionless blockchain in the sense that has to be fully distributed where anybody can participate. So in many cases, people can just use either a centralized or a distributed database instead of a blockchain. And in some cases where you might know all the writers, but maybe not trust them, and that can apply in some enterprise application scenarios, like supply chains, then you might need a public or private permission blockchain, where you have a smaller set of validators that manage the blockchain, so you have a greater degree of trust and you can get more computational efficiency there. So for us, in our recent book, we looked at some of these questions and challenges, particularly in the context of cyber-physical systems. And this book was led by Ali Dori and was also co-authored by Salil Kanir and myself. So the challenge for scalability in blockchain is that it's a peer-to-peer network. So all the participants will receive everything and they need to verify everything. But what that means, it limits the throughput, the transaction throughput of a blockchain. And in this figure, we're just looking at the throughput, the transaction speeds of some of cryptocurrencies compared to Visa and PayPal, which are very much mainstream payment systems at the moment. So, Visa has 24,000 transactions per second, whereas Bitcoin can support only 7 transactions per second by design, in order to ensure that there's no double spending and no other such issues. Now, there are other cryptocurrencies that have a faster transaction rate, but still they don't reach the levels required for becoming a global payment system, replacing the current ones. And the other current issue with blockchain is that it's very energy hungry. So as of recently, Bitcoin mining consumes actually more electricity than 159 countries shown there in orange, including Ireland and most countries in Africa. So it's not sustainable necessarily to continue with these kind of consensus algorithms for blockchain if it is to become a mainstream system underpinning cryptocurrencies, but also for other applications like cyber-physical systems. So in that line, we looked at can we create a more lightweight and scalable blockchain that's more suited towards Internet of Things. And this is a work that we proposed starting in 2017, and we refined for a couple of years. And there we looked at a smart home scenario initially, where you have many devices talking to what we call an OBM, which is essentially a gateway. It's managing the overlay network that is maintaining the blockchain. And we introduced a number of optimizations in LSB, including a distributed time-based consensus, distributed trust, and distributed throughput management. And I'll talk about a couple of them now. So in distributed time-based consensus, the idea is rather than having the validators solve a complex puzzle, we enforce that each validator or miner can only create one block on the blockchain per consensus period. And they also each have to wait a random time before generating a block. And the way we enforce that they have waited a random time is that the neighbors verify the behavior of their neighbors. So it's more a neighbor monitoring type approach. And the way this would work is if you have a malicious entity trying, so in this example, we have the consensus period is 10 minutes, but there's a malicious entity here on the top left that is trying to generate or add blocks to the chain much more frequently, so 1 minute apart rather than the 10 minutes. So what happens is these other overlay nodes that are hearing these blocks actually discard them because they notice that the time between the blocks from this particular node is much smaller than the consensus period. So this is how the neighbor monitoring works in LSB. And the idea there is also because we don't have, in IoT, when we have transactions essentially are maintaining the data records that have happened for auditability, that we don't have issues like double spending, for instance, where in a cryptocurrency, a malicious entity might try to spend some Bitcoin in one location and then to spend the Bitcoin in another, the same coin in another location by exploiting some delays in the network. So here we don't have that issue, and we can relax some of the security assumptions that allows us to have this LSB. And it actually is much more efficient because all that computational cost of solving that puzzle is gone. All you need is to maintain a timer and have some additional packet exchanges. And now I also mentioned distributed trust. Another optimization we had in LSB was that rather than having every node verify all transactions in the blocks it receives from other nodes, we actually adopt something that is inherited from even our trust and social relations. And that if you know somebody and you've had a lot of positive experience with them, you tend to trust them and you tend to be more confident in what they're saying has happened. So in a similar spirit, we in our distributed trust approach, each node can maintain direct and indirect evidence about other nodes in the network. And this evidence is basically looking at the previous transactions and blocks that these nodes have generated, and looking at whether all of these have been verifiable or not. And the more verifiable information I receive from those nodes, the less I need to verify all their transactions. So I can verify a proportion of their transactions. And the table you see there is just an example of a distributed trust table that we used. And what that means is that in some of our simulations, we compared LSB to the baseline, Bitcoin blockchain, and on the x-axis you see the number of transactions that have been, the number of blocks that have been generated versus the processing time, and the gray line is essentially the percentage of transactions to verify. So we see that over time that percentage drops from 100%, where in the beginning nodes don't trust anybody else because they don't have any evidence, to about 20%, around 50 or 60 blocks, where that distributed trust kicks in and the nodes can reduce the proportion of transactions they verify, so they also reduce their computational cost on top of the savings they get from the distributed time-based consensus. So this was LSB. More recently, we proposed another optimized consensus approach for IoT. And this one actually, it's called tree chain. And it embraces the idea of parallel ledgers. So by design, rather than calling it forking, we use parallel ledgers. And the idea is that each validator is responsible for maintaining one particular branch or one particular ledger there. Now, this might seem counterintuitive, but it will make a bit more sense in the next slide. And this was recently published at ICVC in 2021. So the idea is tree chain is a validator selection algorithm. And the key for selecting a validator, the reason why consensus is challenging in blockchains, is that you need to randomize the decision of who is the validator for a block. Now, so tree chain basically uses patterns that are distributed randomly among all validators. And depending on its allocated pattern, each validator commits transactions that fall within that pattern. And all the nodes agree on which of the validators is responsible for which patterns. And because of that, everybody knows their responsibility. So there's actually no need for further interaction to agree on who's going to add the next transaction or block. And we, in our simulations and proof of concept prototypes, we found that tree chain can achieve near real-time consistency in the ledger as well. So the key underpinning tree chain is using hash functions in order to create these patterns that are unique for each validator. So hash functions are random and unpredictable. So you take a message of m of arbitrary length, you put it through a hash function, and you get a hash value h of fixed length. Now the key also is that it's almost impossible probabilistically to go back from the hash value h back to m. So it's very hard to fake a hash. And the interesting thing about hash functions is they're already implemented in all blockchains. So they are we're already paying that cost for them. So the way tree chain works is that we set a consensus code range, which is the most significant bits of the hash function output of a transaction. So we take, it might, depending on the situation, we might take alpha 1, alpha 2 to compare against the consensus code range. It also uses something called the weight dictionary. So for each one of the available characters, we set a weight, which will allow us to calculate what's called a key weight metric. And this key weight metric gives us the cumulative weight of each public key hash. So in this case, we have a node with ID 12 that has this particular, the hash of its public key is this code that you see here. So to calculate the key weight metric, all we need to do is take the weights from the weight dictionary of every character. So A is 37 based on this table, and then X is 60, so and so on, and we add them in order to get the key weight metric of node 12. And we assign, because it has the highest consensus code range, because it has the highest key weight metric, after we repeat the process for all the available validators in the network, then we assign a consensus code range for each of the validators. What that means is that transactions whose most significant bits of their hash falls in this range will be validated by this particular node, and the same for other nodes. So with that, there's no argument about who is validating which transactions. This is all determined based on the hash of the transaction and the hash of the public key of the validators. And these mappings of which nodes get to validate what consensus code range are periodically updated, so that there's no malicious behavior there. And interestingly, this fully randomizes the assignment of transactions to validators. So it makes it very difficult for a malicious validator to target specific transactions or block, because they don't know which one they're going to get. Okay, so that was about scalability in consensus approaches for blockchain and cyber physical systems. Now, the next thing is immutability. And I'm mindful that the conference Wireless Days is based in France, although it's happening virtually now. And in Europe, there was a great regulation, the GDPR, which also is known as the right to be forgotten in more colloquial terms, which was introduced a few years ago, and essentially saying that personal data or data specific to an entity, that entity has a right to ask for it to be removed from servers if they want to. Now, there's obviously a potential tension between that GDPR and blockchain, which is a persistent immutable database. So once the data is there, technically you are not able to remove it. So we looked at this problem, and we introduced actually a type of removable blockchain that was published in FGCS a few years ago, and we also wrote a conversation article about it. And the essence of it's called MOF-BC. The idea there is that rather than keeping data consistent on the blockchain, and by consistent we mean that this chaining of transactions and blocks should not be broken, because that's what really maintains the integrity of the blockchain. So what we do is we remove the data from the blockchain, but keep or even the transaction contents, but we keep the hashes of them as traces that these transactions took place. And the key to doing that is we shift from having the Merkle tree in the blockchain, which is summarizing all the transactions in conventional blockchains, to basically having the Merkle tree represent the hash of all the transaction IDs. And typically these transactions IDs are the hashes of transactions themselves. So what that means is that if we remove a transaction, such as transaction 2 in this example, the hash of transaction 2 is maintained on the blockchain. And if somebody has a private copy of that transaction, they can prove that it indeed maps to this hash of transaction 2. So it still provides a degree of traceability, and it does not break the consistency of blockchain, but it allows us to remove the content of transactions on the blockchain. All right, now we're moving to the topic of trust. And there's quite an interesting problem when we deal with non-cryptocurrency applications of blockchain, is how do we trust data written into the blockchain? And there's typically what's known as the garbage in, garbage out problem. Now, this problem is about if blockchain gives you immutable storage. Once the data is stored, you can be sure that nobody will change it and that it is reliable. Now, what happens before the data stored on the blockchain is dependent on how it's collected. And cyber-physical systems, typically that's through sensors or other data sources. And there's a lot of potential for malicious entities or noise or bias to enter into that process. So we identified the need to have some cross-validation of data that's entered into the blockchain and some assessment of how much can we trust this data once it's stored in the blockchain, so that we're sure we're storing something reliable, or if not, that we're estimating how reliable it is. So the network model we used there was you have a bunch of gateways similar to LSP that are part of the blockchain overlay network. And for each gateway, you have sensors that are connected to it. And the architecture we came up with essentially tries to propagate trust from the data layer through to the blockchain layer and into the application layer. Now, the trust at the data layer tries to take into account how much other sensors nearby are corroborating the readings of this particular sensor, the reputation of the sensor, so historically, how honest has it been? And a sensor might also have an estimate of its own confidence in its observation. For instance, in localization, you might have a sensor telling you, here's the uncertainty in my ranging or localization measurement. So we capture all of that and add it into the transactions that go on the blockchain. And then we also use that in our distributed trust approach that I mentioned earlier for the gateway reputation and management of the blockchain. Now, a bit more detail on the trust and reputation mechanism. So as I mentioned, trust is considering 3 elements. These are the evidence from other observations. So if a neighbor sensor node support or does not support the observation, it will affect this particular metric depending on the sensor's own confidence in its measurement. There's also the reputation of this sensor previously. So how much evidence do we have that this sensor has acted correctly in the past? And as I mentioned, there's also the sensor's own confidence in its measurement. So here's just an example of an RSSI-based localization approach, where we simulated some malicious nodes measuring the received signal strength indicator. And the malicious node, essentially all these nodes were in the same physical area, but some of them were reporting much lower RSSI than most of the nodes. And so we essentially, this trust approach penalizes the malicious nodes because their measurements move away from the measurements of the majority of nodes. And this causes their trust to drop significantly, and it takes them longer to recover that trust over time. All right, so we looked at scalability, immutability, and trust. And through that, we also looked at applied these approaches and these ideas in various vertical applications for CPS, including supply chains, energy trading, smart vehicles, and manufacturing and digital twins. And in the remainder of the presentation, I'll just go through 3 of these applications in a bit more detail. So first, let's look at supply chains. And we identified a few challenges there. And this work actually is, much of it is PhD work from Sidra Malik, my joint student with Salil Kanir from UNSW. So there we identified issues about provenance, trust, data, and identity. So in provenance, we looked at issues of governance of a supply chain and how can it scale. On trust, we looked at accountability and reliability of the information, similar to the trust architecture that I just presented. And we also looked at the data and what data can be revealed and what data should be kept secret, and similarly about the identity. So for all of these different considerations, we progressively looked at different blockchain approaches for solving these problems. So we'll start with the product chain, which was essentially to provide provenance in blockchain-supported supply chains. So it used a permissioned ledger where you have an access control list of the participants, and you also had some non-participating members, such as, for instance, the consumer. So in this approach, we defined a network model, which included these participants and non-participants. It used side chains in order to support geographic diversity, and also the product ledger, which was the tier 3 in this figure here. We also looked at, we defined the transaction vocabulary, so capturing the details of creation of a product, its transfer from one supply chain entity to another, its production and manufacturing, and then also its final sale. So through that product chain, we could do things like you'd have tags on a final product that sold to a consumer, and through the blockchain, you could have full visibility into the product story. In this case, there's a chocolate bar that was purchased, and the consumer can scan that and get information on the various steps that it went through, including where it was manufactured. And at the time of manufacturing, it actually combined milk and cocoa because it's a composite product of different base products. And you can also branch out from that production level to the different sources of those base products. So that was about provenance and product chain. But then we realized also that there is potential for things like sensor data or other data reported by supply chain participants to be misrepresented or just faulty. So at that stage, we introduced trust chain, which was integrating some of the trust concepts into the supply chain scenario. So in trust chain, we rely on multiple source data observations at the data layer, including sensors, even things like regulatory bodies saying, affirming that some products were the right quality, and the observations of traders themselves. So at the blockchain layer, we introduced a reputation and trust module and various smart contracts in order to capture the quality and rating of the different entities and products. And at the application layer, we have queries in order to retrieve the product story, and things like rewards and penalties that come into play when trust and reputation, go up or down. So then after that, we looked at privacy, and we realized that one barrier to blockchain adoption and supply chain is that many of the participants prefer to keep their data, a lot of their data, secret. So there's a tension there between the need for traceability and auditability, and also the privacy or commercial sensitivity of some of that information. And so there we relied on zero knowledge proofs, which are cryptographic methods in which a prover can attest to a verifier that some secret information is true without revealing any information about the secret. This can be something like proving that the product was created in a certain region of France, for instance, without revealing necessarily the particular farm on which it was produced. Or it may be that a particular supplier or particular logistics company has not taken the product through a territory which is against the production cycle of that product, but maybe doesn't want to reveal the exact route of where that logistics company went. We also rely on Pedersen commitments, which is a non-interactive secret sharing scheme, where a user can commit a secret. It can send the verifier a commitment to the secret without disclosing the secret itself. So this one, we used it in order to incentivize the supply chain participants to provide the zero knowledge proofs and maintain the blockchain. And there this is kind of a contract where producers and supply chain participants can get back monetary incentives for spending that effort in providing those proofs and verifying those proofs. So the way the architecture works for PrivChain, which is currently still under review, is that first the blockchain, the supply chain participants can provide their proofs and store them on a blockchain. And these can be verified, for instance, proof of origin, and the results of that verification can be stored on the blockchain as well. And then the request can go to a bank to give the incentive payments for those based on those Pedersen commitments that we talked about. Now, a consumer who accesses the QR code, for instance, on a bottle, which we would have imprinted the origin in the QR code, can simply scan that code and then through the blockchain verify that proof of origin. So the idea there is verifying things like region of origin or other attributes without revealing the details of those attributes. Now, we also propose another way to preserve privacy in supply chains, which we call trade chain, and this is appearing at TrustCom next month. So in this approach, we separate the storage of identities in one ledger, which is called IDML. And we also have the trade management ledger, which is storing the trades. So a trader is first onboarded onto the identity management ledger, but then trades over the trade management ledger. And then a requester who wants information about a particular trade, they can request a token from that trader. And then if the trader grants them access, they can use they can issue a query using that token through a smart contract in order to fetch the details of that trade. And the key here is that to decouple, in a way, the identity information from the trade information in the two ledgers. All right, so that's about supply chains. Next, let's move on to connected vehicles. And there, it's connected and autonomous vehicles are certainly an area where the data tsunami really kicks in, because they have a wide plethora of sensors that will be and are generating a lot of data all the time. So they also have significant security risks. There was this famous story back in 2015 of some white hat hackers remotely hacking a Jeep and taking full control of it. And with increased autonomy of vehicles, that's going to be a bigger concern as well. So the first thing we did was we applied an approach very similar to LSB to the automotive security and privacy, where you will have these overlay nodes managing the vehicles, and the vehicles might move around between them depending on where they are. So one example of how this would come into play is that in this case, it's about a wireless remote software update. So you have a software provider that wants to provide an update to the firmware of a connected and autonomous vehicle. So the first step is that provider first stores that update, and then what happens is it sends a multi-sig transaction to the blockchain until it reaches the OBM that is responsible for this OEM, so for the manufacturer of this vehicle. This is countersigned by that manufacturer, and then what happens is that once that's all been signed by all the relevant parties, we have that's forwarded to the OBM responsible for the vehicles that notify them of the update so they can download the update. Now, the other question we looked at also was who's to blame when driverless cars have an accident. And at the time, that it was a time where Uber, one of the Uber self-driving vehicles, had killed a pedestrian in the US. So in that case, we looked at a blockchain framework for insurance claims and adjudication. And the idea there was that you keep as many transactions of the vehicle's events as you can on the blockchain through. So we actually separated the blockchain into an operational partition that include things like service technicians, auto manufacturers, and the vehicles themselves, from a decision partition that includes the authorities, government transport authorities, legal authorities, and the insurance company. And the idea is that the vehicles store events on the blockchain as they occur, including accidents, speeding, driving behavior. And these are maintained and agreed on in the operational partition. But then if something happens, like an accident, then that is all that data is reported to the decision partition to decide on who's to blame in that case. And here's just an example of a 3-car collision where initially the vehicles generate data related to the collision and store it on the operational blockchain. And then the participants to that blockchain report the data and agree on it, but also report it up to the decision partition, where the various data is taken into consideration in order to decide liability of the various parties. All right, now we'll go to the final application I'll talk about, which is energy trading. And our motivation there in looking into this area for blockchain is that there's a significant growth in renewable energy sources. In Australia, we have a lot of solar, but I know in Europe, there's a lot of wind farms and other renewable energy coming into different parts of the world. And that actually motivates trading energy between consumers who have now become producer consumers or prosumers with other entities, because typically the grid is a very centralized network that's centered around the energy company. So with blockchain, we have an opportunity to actually provide a decentralized or distributed energy trading approach if we can address some of the challenges there. Some of those challenges are the lack of privacy. So you don't necessarily want everybody in the network to know who you are or what your energy production or consumption patterns are. And also, a lot of the existing methods that use blockchain for energy trading still have a trusted third party. So there's still a degree of centralization there. And also, you have blockchain overheads for negotiating prices of energy, which need to be taken into consideration. So for that, we proposed secure private blockchain-based energy trading, which introduced an anonymous routing method on top of blockchain, and a purely distributed trading method introducing what we call atomic meta transactions. And also, we introduced a certificate of existence that allows you to privately authenticate smart meters to verify that they are indeed smart meters. So for the anonymous routing backbone router, the idea is it uses the public key of the devices to decide who's going to be the router in the network. So we have these high resource available devices in the backbone that route the packets, but then rather than purely relying on IP-based routing, we use the public key to decide the next router for these nodes on the backbone network. Now, the next one was this atomic meta transactions. And there we wanted to make sure that the customer doesn't pay the money and then not receive the energy. So the idea was to split these X1 and X2 on this figure are actually two transactions that form a meta transaction. So first, the customer commits to pay a certain amount for a producer after their negotiated price. And then the producer sends the electricity to the customer. And once it has done so, then the customer can confirm receiving the energy, and the blockchain releases the money that would have been frozen from the customer, but not transferred. At that point, when the energy is received and it's confirmed by the customer, the blockchain releases the money to the producer. We also have the certificate of existence, which is a way to verify the authenticity of a smart meter. And the idea there is that the meter manufacturer can assign public-private key pairs to each meter, and it serves as the certificate authority for those keys. And every meter can form a Merkle tree of its public keys. So essentially, it can iteratively hash its public keys and come up with a Merkle tree root for that. So it uses that root to another meter to be signed. Now, the key there is that that other meter is selected randomly from the available smart meters in order to avoid attacks. And the signed root will be used as a certificate of existence. So going that into a bit more detail here, we have step one where the smart meter generates n public and private key pairs, and there are some trade-offs on the number of those pairs. It forms a Merkle tree of those keys. Then it sends a verification request to a verifying meter. And that other meter is chosen randomly. So that other meter, what it does is it verifies that the public key used in this verification request is indeed of an authentic meter. And the way it does that is it simply queries the certificate authority, which is the manufacturer in this case. If that checks, then it signs the root of the Merkle tree, which was sent originally by the smart meter, using its own private key, and it sends it back to the smart meter. Now, in step 6, what happens is that that certificate of existence, which was signed by the verifier meter, is entered into the transaction. And what the smart meter does after that is it provides all the hashes in the Merkle tree that are required to verify the certificate of existence signature. Remember here we talked about this root, and Merkle tree is the interesting feature about them is it's easy to verify the existence, for instance, of A if you have the hash of B and the hash of CD in order to prove that the hash of A is part of this tree. So all these other hashes are sent in the Merkle tree, are sent in the included in this transaction, and then this transaction is signed with the private key that corresponds to the public key that we want to use for the energy trading. And then that's sent to the blockchain participants, which confirm that the price is the agreed price. They confirm that the public key is valid by checking with the certificate authority. They confirm the existence of the public key in the Merkle tree, and this is done by including those other hashes in the transaction. And it makes sure that the public key matches with the transaction signature. And if all that checks out, then we can verify this as a true smart meter. Now, building on that, we also looked at how can we add location awareness to energy trading. And the idea there is if you have a pure peer-to-peer energy trading system supported by blockchain, then you might have very inefficient flows of energy, because if people find the best price really far away, then you will have a lot of load on the grid with that trading happening. So the idea there was to maintain a decentralized market, but to also prioritize other nodes that are closer by for having energy transactions. But we also wanted to maintain anonymity. So we provide a novel anonymous proof of location algorithm to prove the location of agents. And so the idea from a high level, similar to building on the certificate of existence, is that we have the certificate authority, which could be the energy company in this case, providing the public keys. In this case, smart meter A wants to prove its location anonymously to other participants in the network. So similar to before, it requests a certificate of location from a randomly selected smart meter B. And with that, it also includes a noisy version of its location. So that might be a street or neighborhood level. So enough resolution in the location to be significant for the grid operation, but not to reveal, for instance, the address of this smart meter. Now, then this is once it receives that request, this smart meter verifies the public key of the smart meter A, sends a certificate of location, and similar steps to before. This smart meter, when it wants to trade and share its certificate of location with any other smart meter C, it can do so, and that can be verified by smart meter C. So that's about the anonymous proof of location. So that actually brings me to the conclusion. Actually, before that, we have some results from that approach, where we simulated a grid with different consumers and producers. And also we implemented the blockchain part on Raspberry Pis. And we found that with this approach and the ability to verify anonymously the location of different nodes, we found that there's a significant preference of nodes to trade with nearby agents, which ultimately will be better for the grid and more efficient. So just to conclude, it's still early days in this area of applying blockchain to cyber-physical systems. There's still a lot of research that can potentially be done, ranging from mathematical models of blockchains, ways to improve scalability and performance, new architectures, applications, and thinking about how machine learning can play into blockchain and smart contracts as well. And also in terms of disciplines, there's a lot of research opportunities in the area of security, distributed systems, networks, software engineering, and many more. So before I conclude, I just want to acknowledge the many collaborators that have contributed to this effort. And I'd like to thank them all for their contributions. And just a list of references in case you'd like to follow up in more detail on the things I talked about today. Thank you very much.
Thank you very much, Raja, for this very interesting talk